Welcome back to AICE Chemistry lecture series. In this video, we are going to go over chapter 3, section 5. Now, the topic of this section is mole calculations. This has anything having to do with conversions between moles and mass, volume, particles, as well as between different compounds. Now, in this section, this is going to get very complex and very tedious. Why? This is where we put everything we learn, mathematics speaking, from honors chemistry into one particular section and into a bunch of different math problems. Now, this section is not complicated because you're going to learn many new things, because you're not. Everything we're going to cover here really comes from honors chemistry, but the logic and the critical thinking behind these questions are what are going to be very challenging for a lot of you. So you have to be very careful, because if you don't understand the question here, if you're looking at a question saying, oh, I never learned this, chances are you probably did learn it, but you're not looking at the question in the correct manner. You're not using the correct logic and critical thinking behind this question, because you're putting together a lot of different material, especially from the second half of honors chemistry. So let's dive right into this. So reacting masses. When trying to calculate the mass or moles of a chemical reacting a chemical equation, we have to use what we call stoichiometry. Stoichiometry is the mole ratios of reactants and products shown in the valence equation. So when we have stoichiometry, when we talk about the word stoichiometry, when something requires stoichiometry, we are essentially talking about converting between moles of one substance to moles of another, using the mole ratios shown in the chemical equation. So, for example, here we have iron 3 oxide reacting with carbon monoxide to form iron and carbon dioxide. In this particular equation, we have 1 mole of iron 3 oxide reacting with 3 moles of carbon monoxide to create 2 moles of iron and 3 moles of CO2, carbon dioxide. Those are the coefficients in this equation. So we have a 1 mole of iron to oxide ratio to 3 moles of CO to 2 moles of iron to 3 moles of CO2. We can use this ratio to convert from moles of one compound to moles of a different compound, or element in this case. So we have to be able to think of those numbers and how we can use them. Now, the other part of this is that these are not always going to be direct mole-to-mole conversions. If we needed to go from grams of iron 3 oxide to volume of CO2, for example, that would still involve these coefficients, these mole ratios, but as well as other conversions like molar masses and Avogadro's constant, or Avogadro's hypothesis, and using the molar volume. In order to do stoichiometry calculations, we usually need the mass of one chemical, or I guess a volume or number of particles. So we're going to include a lot of other concepts with these problems, with this what we call stoichiometry problems. So stoichiometry problems can be very complex because they're going to include a lot of different material. So before you even start looking at this section, make sure that you are able to balance equations and to understand what coefficients are from honors chemistry. So stoichiometry, like I said, can require a lot of high-level critical thinking in order to figure out. Because, for example, in this chart, we can see all of the different conversions we could possibly use. Now, this is not a complete list. This is just an idea or an example of all the different things that you could be asked to do in the AICE exam. So, for example, we could be asked to convert from moles of one substance to moles of a different substance by using those mole ratios that we talked about, a mole-to-mole conversion, using the coefficients, using the stoichiometry and the balanced equations. So that's the first and foremost what's going to be at the center of these conversions that require reactions, is the conversion of moles of one substance to moles of a different substance using those ratios. We could also, before that or after that, be asked to convert from moles to either atoms, formula units, ions, or molecules, or vice versa, from in any of these two moles. And that's going to require us to use Avogadro's number that we talked about earlier in this chapter. Using Avogadro's number, we can transform moles to atoms for any element, formula units for any ionic compound, ions for any ion, and molecules for any covalent compounds, what we normally call molecular compounds. So we can use that number, that conversion factor, Avogadro's number, to transform moles to any of these or vice versa. We can also be asked to go from moles to grams or milligrams or kilograms by using the molar mass of a substance, which we get from the periodic table. So we could convert from moles to grams by using molar mass, and then from grams to milligrams or kilograms by using the metric system. 1 kilogram is equal to 1,000 grams, 1 milligram is equal to 1 gram. And we could go backwards as well. We could go from milligrams to grams to moles, or from kilograms to grams to moles, or vice versa, using again that conversion factor of the molar mass. We also learn, and we're going to recap later in this chapter, but we also learn in honors chemistry how to go from moles of a substance to volume in liters when it's a gas. We learned that using RTP in our case, so this will be slightly different because Cambridge does not use STP. We use RTP, and we use 24.0, not 22.0. But we use 24.0 liters to convert from moles to volume in liters of a gas specifically, using 24.0 equals 1 mole. Now this has to be under RTP, which if you remember is 25 degrees Celsius and 1 atm of pressure. But we can do that conversion for moles to liters of a gas, and then from liters to milliliters, or which will actually be cubic centimeters since we're in Cambridge, to cubic centimeters, or to cubic decimeters using the conversions we have here, which are metric conversions. We could also go this way, which we'll talk about in chapter 6. All of these that we have here is conversions between moles and energy. Now we can't do this yet because this is going to be from chapter 6 later in the year. But we could also add to this something we did learn last year, which is a conversion between moles and liters, or the m cubed, of a solution. And we convert to moles of the n cubed of a solution using the concentration. And remember, concentration is moles per the m cubed of a solution. So we can also add this to the list, along other things that we will learn later in the year, like PV equals nRT for non-ideal gases. But we'll talk about that in chapter 4. All right. So for now, we won't look at that particular part. I'm actually going to cross it out because we won't look at this yet. That's in chapter 4. And this is in chapter 6. So let's look at this problem. Now, this is the continuation from the problem that we did in section 4. Here we are asked to calculate the mass of hydrogen present in 0.54 grams of H2O. And this is going to be kind of continuing from what we did earlier. It's very similar to the problem we did earlier, but we want to kind of cover our bases here. So let's look at this question. Now I'll bring it over from here. So calculate the mass of hydrogen present in 0.54 grams of H2O. Use the value to calculate the amount in moles of hydrogen atoms present in 0.42 grams of A. So this question kind of has two parts here. We have, I'm going to move this. We have the calculation of the mass of hydrogen ions present in H2O, in 0.54 grams of H2O. Hydrogen atoms, not ions. And then we have the second part, which is to transform that into particles. So this part right here is actually from section 4, but then this continuation to this is from section 5. So let's look at that. So just to recap, in order to figure out the number of the mass of the H2O here, we have to remember that if we have 1 mole of H2O, because of that 2 represents that there are 2 hydrogens for every 1 mole, or 2 moles of hydrogen for every 1 mole of water, that means that we have 2 moles of H to 1 mole of H. That's our conversion factor. So here we have 0.54 grams of H2O. If we divide that by the molar mass of water, which if we bring our periodic table, we can look at the molar mass of water here. We have oxygen has a molar mass of 16, whereas hydrogen has a molar mass of 1. So H2O, H has a molar mass of 1.0, but there are 2 hydrogens, that means 2.0. Oxygen has a molar mass of 16. It's only 1 oxygen, so plus 16.0. That means the molar mass of water is 18.0. And this is what we're going to use for Cambridge. This is the Cambridge periodic table, so we're going to use these numbers with 1 decimal place. I know that if you look at a different periodic table, this would actually be 1.01. But again, we do use the Cambridge periodic table to do this, since it's what we're going to use in the exam. So, the molar mass of water here is 18.0. So, we know the molar mass of water is 18.0 grams of H2O. Is 1 mole of H2O. Let me make this a little smaller. Times. Now this is where this comes in. 1 mole of H2O is equivalent to 2 moles of H. Again, this comes from the formula for water. H2O, meaning that there are 2 hydrogens in 1 water. So if we have 1 mole of water, we have 2 moles of hydrogen. And then in order to turn this to grams of water, then we need to say that 1 mole of hydrogen is equal to 1 gram of hydrogen. Again, this coming from, let me clean that up a little. This is coming from the fact that the molar mass of hydrogen is 1.0 grams per mole. So we have 0.54 divided by 18 times 2 times 1. Let's bring up our calculator here. 0.54 divided by 18 times 2 times 1, which we already need to do, is 0.06. So we have 0.06 grams of hydrogen in 0.54 grams of water. Now here, the next part says, use this value to calculate the amount in moles of hydrogen atoms present in 0.42 grams of A. Now we could have stopped here, right? Because for what they're asking us to do here, we actually need moles of hydrogen, not grams of hydrogen. So we could have stopped right here. The problem with doing that is that this question says, let me use my highlighter. This question says use this value to calculate. So they want us to start from that 0.06 grams of hydrogen. So we can't just ignore that. We do need to start from there. So we're going to start from 0.06 grams of H as our initial point. And we're going to calculate the amounts of moles of hydrogen atoms. So these are the grams of hydrogen atoms. We need to convert this to from grams to moles of H. So in order to do that, we need to again divide by 1.0 grams of H is 1 mole of H. So 0.06 moles of H, thanks to the molar mass of hydrogen being 1. So use this value to calculate in the amount in moles of hydrogen atoms present in 0.42. Well, that's pretty much it. That's the amount in moles of hydrogen atoms. So that is what our final answer would be. Now, this is redundant, and we did not need to necessarily do this. But when you're unsure, when you have wording like this, use this value to calculate, then you want to make sure that you're just covering your bases. And this does not take any much more time. I mean, it's about a few seconds more. So let's look at the mark scheme here. So if we look at the mark scheme, we'll see that we did need to show it because we have 2 points to this question. The first point is for the mass of hydrogen being found. So we have that, again, we did it in the dimensional analysis way, but you could have done this any way as long as the math is correct. We have that 0.06 grams of hydrogen from the first part of the question. And then the second point is actually for grabbing the number and dividing it by 1 to get the moles of hydrogen. So had you not actually followed this, had you not pay attention to this, use this value to calculate, you actually would have missed out on a point. So it is very important. Again, you don't need to show the dimensional analysis. As long as your math makes sense, they're okay with it. But it's the exact same answer numerically, but because they say use this value to calculate, and it's really just a division by 1, you need to do both parts of the work. Remember, it's not necessarily about the question being complicated, but it's about you following what they're asking you to do and actually answering the question the way they want you to answer the question. So let's look at another one, another question, but let's look at a question from paper 1. This question now says, the nitrates of beryllium, calcium, magnesium, and strontium all decompose in the same way when heated. When 2.00 grams of one of these anhydrous nitrates is decomposed, 1.32 grams of gas is produced. What is the nitrate? Now this is, even though it's a paper 1 question, which is multiple choice, this is a more complicated question because it incorporates 2 things. One is knowing what the decomposition reactions of these nitrates are, and I'm going to give those to you in a second, because it's not something that we have covered yet in AICE Chemistry, although we did cover in honors chemistry. And then it also includes us doing the mathematics associated with this. Now, one thing I did want to point out about this question is that it says, use your data booklet. Now, data booklet is an old thing that we used to use. Now we'll say something like use the periodic table. But all this means is use your data booklet means use the periodic table, because you're going to need the molar masses of some of these. So don't be afraid when they're telling you use your data, or use the periodic table, use your reference sheet. Sometimes is what he'll say, because sometimes, a lot of the time, it just means, use your periodic table in order to do this. So again, let's look at the question in a separate format so that I can write on it and show you properly. So here we have the problem, and I have actually included, even though from honors chemistry you should be able to kind of figure this out, although it is really hard, and we'll cover this when we do group 2 elements in the inorganic section of the curriculum. But here are the reactions, the decomposition reactions for all 4 of our answer choices. Beryllium nitrate decomposes, or 2 beryllium nitrate decomposes into 2 BeO, which is the beryllium oxide, plus 4 NO2 plus O2. Now you'll notice that all of these have the exact same reaction, except the metal changes. Why? Remember that elements in the same group have similar properties. That means they make the same compounds and they react in the same way. So you can see here that says the nitrate of beryllium, calcium, magnesium, and strontium all decomposes the same way when heated. Why? Because they're all group 2 elements, they're in the same group. When 2 grams of one of these anhydrous nitrates decomposes, we get 1.32 grams of the gas produced. So there's a few things to break down here. First of all, we need to know the states of matter, because we get that it says 1.32 grams of gas is produced, meaning all of the gases. What are the gases here? Well, all of our group 2 nitrates are going to be in the solid state. And this is where the critical thinking kicks in and where this can be very difficult for some of you. How do we know these are all solid? Well, think of the kind of compounds they are. We have a metal with a polyatomic ion. These are all ionic compounds. Ionic compounds we know are solid at room temperature. All of them without exception. We then get the oxide of these elements, of these group 2 elements. Well, these are also solid. Why are these solid? Because, again, they are ionic compounds. We have a metal with a non-metal. And so these are all ionic, so they're always going to be solid. NO2 is a gas at room temperature. It's something that you'll learn with time. But nitrogen dioxide is gas. And then oxygen is a gas at room temperature. So when they say we have 1.32 grams of gas produced, what they're essentially saying is that between the nitrogen dioxide and the oxygen, we have 1.32 grams produced. And that we decompose 2.0 grams of the nitrates. So that's first of all. So there are actually two ways of doing this question, because this is a very really high level critical thinking question. And there are two ways of doing this: a smart way and a really smart way. And I'm going to show you both of them. Now, the smart way, which you should always do with these multiple choice questions in paper 1, is to use the answer choices, A, B, C, and D. So we know our options here. So how can we do this in a way that's not going to take some high level complicated math? We can simply figure out how much of each of these things will be given by 2 grams of each of our options. Once we get 1.32 grams, that's the answer. So if we start with beryllium nitrate, that means that we have 2.0 grams, and I'm going to do this in a bit of a shorthand notation, 2.0 grams of BeNO32, molar mass of beryllium nitrate, and that's one of the things that we need to figure out if we bring our periodic table over. Molar mass of beryllium nitrate, we have here, I'm going to use my so our molar mass of beryllium nitrate would be, beryllium's molar mass is 9. Ooh, that is a big circle. So let's do that again. Beryllium's molar mass is 9. We have BeNO32. So we have 9, nitrogen is 14, and oxygen is 16. So we have 9 plus nitrogen, which is 14, but it's times 2, so 14 times 2, plus oxygen, which is 16, but 16 times 3 times 2 is 6 different oxygens. So that's 9 plus 14 times 2 plus 16 times 3, or times 6, sorry. So let's see what this is here. 9 plus 14 times 2 plus 16 times 6 gives us 133 is the molar mass of beryllium nitrate. So it's 133.0. So let's go back and put that into our work. And I'm actually going to write this down because it's going to become important later on. So it's 133.0. I'm going to go ahead and write that here. So 133.0. 133.0 grams of, and I might just use quotation marks to say beryllium nitrate, is 1 mole of beryllium nitrate. Now, we know 2 moles of beryllium nitrate, according to our equation down there. Oh, let me just use the quotations again. So 2 moles of beryllium nitrate is equal to 4 moles of NO2. Oops, forgot the mole. And the molar mass of NO2 is 1 mole of NO2 has a mass of 16 times 2 is 32, plus 14 is 46. So that's 46 grams of NO2. So that's 2 divided by 133 times 4 divided by 2 times 46. Again, that's 2 times 4 times 46 divided by 133 divided by 2. That gives us 1.38 grams. So that's 1.38 grams of NO2. Now, what we would need to do in order to figure out how much this is combined with oxygen is that we need to do the exact same thing. So 2.00 grams of beryllium nitrate times 133.0 grams of beryllium nitrate, 1 mole. But now we're converting this to oxygen. So we have that 2 moles, or I don't know why I put 0.0 there, but 2 moles of oxygen, or 2 moles of beryllium nitrate, is equal to 1 mole of oxygen. Again, that comes from the coefficients in the equation. And then the molar mass of O2 is that 1 mole of O2 is equal to 32 grams of O2. So if we did that, that's 2 times 32 divided by 133 divided by 2. That is a 0.24 grams of oxygen. 0.24 grams of O2. So together, the gases that 2 grams of beryllium nitrate give is 1.38 plus 0.24. That's a 2, carry over the 1, 5, 6. So that's 1.62 grams of gas that the beryllium gives. Our question says that 2 grams of the anhydrous nitrate gives us 1.32 grams, so beryllium is not the answer. So we now need to do the same exact thing, but for calcium nitrate. And if that one's not it, then we need to do the exact same thing for magnesium nitrate. And if that's not it, we need to do the exact same thing for strontium nitrate. This will take you forever if strontium nitrate is the answer. Now, if we wanted to be smart, we would have realized that the minute we get 1.38 grams of NO2, that cannot be the answer, because that's already more than the 1.32 grams of the gas in total was. But this can get really, really tedious and really, really long. So let's look at the smarter way of doing this, because there is an even better way of doing this. Even though we are using here our answers, there's a much better way of doing this, which is by using ratios. And that is kind of what the AS exam is asking you to do here, because if you did it this way, it will take you too long. So let's look at this using ratios. Now, what do I mean by using ratios? Well, here we are looking at the conversions of 2 grams of an anhydrous nitrate to 1.32 grams of gases. Well, we can look at the ratio that the molar masses of these different compounds will do or will get with the gases in order to figure out the answer. Oops. Make sure I don't delete things. So, what do we mean by that? First of all, let's get the ratio between our information that's given. So we have 2 grams of the anhydrous nitrate creates 1.32 grams of the gas. That means that if we do nitrate divided by gas in mass, that should give us a ratio of 2.00 divided by 1.32 is, I'm going to bring over my calculator, 2 divided by, 1.32. That gives us a ratio of 1.52, roughly, 515. So this is a ratio of 1.515. That means that if we use the molar masses of the different nitrates and do a ratio between those molar masses, which are masses, and the combination of the molar masses of the gases, that should give us the same ratio for the right answer. Now, when we do this, we need to take into account the ratios for the coefficients. What does that mean? That means that when we do this math, these ratios, we need to take into account the fact that we have 2 beryllium nitrates, 4 nitrogen dioxides, and 1 oxygen. So, that means that we can do a ratio between 2 times the molar mass of the nitrate and then compare that to the molar mass of the 4 NO2s and O2. So, if we look at that, we have, and let's do this in a different color, so purple. So we have 4 times the molar mass of nitrogen dioxide, which is 14 plus 16 plus 16. So that's going to be 46. So we have 4 times 46 grams per mole. Again, why is this? Because we have here the molar mass of NO2, and we create 4 NO2s in the reaction, plus the molar mass of O2, and we only have 1 O2. And this should be a little lower, actually. So, plus 1 times the molar mass of O2, because we make 1 O2. Molar mass of O2 is 32 grams per mole. So when we do 4, and we'll bring back our calculator here, 4 times 46 plus 32, that's 216 grams per mole. 216 grams per mole is the molar mass of all of the gas that's created. So that's the bottom part of this ratio, the gas part. So all of these, when we do them, we're going to divide by 216 because that's the molar mass of the gases put together. So divided by 216, divided this one by 216, divide this one by 216. Now, what are we divided by 216? If this is the molar masses of the gases, then because this was the grams of the anhydrous nitrate, we need, and I'm doing red actually, we need to divide the molar masses of the anhydrous nitrates by this. But we need to multiply by 2. Why by 2? Because all of the anhydrous nitrates are multiplied by 2. So here we have 2 times 133. If we do that division, then what we get out of it is the ratio. And if that ratio matches or is very close to what we are looking at up here, then we know it's the correct ratio and therefore the correct answer. So we do 2 times 133, 2 times 133 divided by 216, that gives us 1.231. So 1.231 is the ratio here if we had used beryllium nitrate. Since we don't have that be close to what we're supposed to get, we know then the answer is not A. And let's do that for all 3 of these. So we need the molar masses for all of the different compounds here. When I bring over our periodic table, again, I'm going to show you a trick to making the calculation of those molar masses easier. So the next molar mass that we're going to need is the calcium nitrate. So we have calcium, and then I'm going to change the color real quick. We have calcium nitrate, CaNO3, and when we do molar mass of calcium nitrate, we're just going to do the molar mass of calcium, which is 40.1, plus the molar mass of the nitrogen times 2, which is, oops, let me do a different color here. Molar mass of the nitrogen times 2, let's do this in pink. So that's 14 times 2 plus the molar mass of the oxygen, which is 16 times 6, because 3 times 2 is 6. Now, this right here is the molar mass of the nitrate times 2. 14 times 2 plus 16 times 6. So we bring our calculator over. That's 14 times 2 plus 16, times 6. Molar mass of the nitrate times 2 is 124. So we're going to put that right here, 124. We add the 40.1 to this, we get the molar mass of the nitrate, which is going to be 124 plus 40.01 is 164.1. So that's the molar mass of the calcium. Well, what if we want to do magnesium nitrate? Well, we don't need to do this part over and over again, because what is magnesium nitrate? Magnesium nitrate is just MgNO32. So it's the exact same formula, except that our metal changes. So what is the molar mass of this? It's simply, again, that 124 we had for the nitrate times 2. And then instead of the mass of calcium, we need the mass of magnesium, which is 24.3. So 24.3 plus 124, that's going to give us 148.3. We want to do this for strontium nitrate, which was the other one. Same thing. SrNO32. Because again, these are all group 2 elements, so they all form the same compounds. That's something you need to start getting used to, because it's going to make your work a lot easier. So again, we want the molar mass of strontium nitrate. It's the same 124 for the nitrate. We just need to change the molar mass of the metal to that of strontium, which is 87.6. And so that, and I can do the math in my head because I'm not that smart. So 124 plus 87.6 gives us 211.6. So here we have 211.6. So you see how that much a lot faster. 211.6. That was a lot more faster than having to do the whole math over and over again. If we just know this is 124, we can change the metal and just add the molar mass of the different metals. So now that we have that, and I'm going to get rid of these real quick. So now we have the molar masses. We can go back to our problem here. We have that the molar mass, it's kind of hard to read because it overlaps, but molar mass of calcium is 164.1. Let's do this in red. 164.1. Molar mass of magnesium nitrate is 148.3. Molar mass of strontium nitrate is 211.6. So now that we have those, all we have to do is multiply those molar masses times 2, because again, there's a 2 coefficient in every single one of the reactions here. 2 times 164.1, 2 times 148.3, 2 times 211.6, and then get those ratios, whichever ratio of the 2 times the molar mass divided by the molar masses of the gases multiplied with their coefficients, whichever one gets closest to this, that's our right answer. So if we do that, and I'm going to bring back my calculator over here. If we do 2 times 164.1 divided by 216, we get that the answer here is actually really close. Oops, let me calculate it one way. It's going to be 1.519. 1.519. So that's really close to our answer, to our ratio here for the numbers in the problem, 1.515. If we do it for magnesium, then we get 2 times 148.3 divided by 216 is 1.373 farther away. Oops. 1.373. Again, farther away from our ratio from the question. And then if we do it for strontium, you can imagine that's why even farther because of that 211. 211.6 times 2 divided by 216 is 1.959. 1.959. 1.959. So you see how only one of these is actually gives you a close ratio, which is the calcium nitrate, which is B. So doing this by ratios is actually a much better option than doing the whole stoichiometry for each one of those answer choices. That can be very, very tedious. Now, will you get the right answer? Yes. Will it take you more time? Also, yes. And remember, in the Cambridge exam, in the AICE exam, timing is a big part of what you're trying to get down. Because if your timing is off, you're not going to finish the test. So whenever you have this kind of math, which is all based on molar masses, especially when you're working with the compounds of the same group, like we're here, use ratios to make your life easier. Now, this is not something that is very logical. It is a very math-based way of doing things, but if you can master it, it will make your life so much easier. And in fact, there's actually an even easier way of doing this, because if we know that the gases, and this, again, I'm not going to actually walk you through this, but it's just to show you that there's actually a million ways so we can do this mathematically. If this is 1.32 is the mass of the gases, the only thing that's not a gas that's left is that beryllium oxide, calcium oxide, magnesium oxide, and strontium oxide. We can actually get a ratio between the nitrate and the oxide, because if we have 1.32 grams of gas, 2 minus 1.32, because we originally had 2 of the reactant, that is 0.68. That's 0.68. If we do a ratio of 2.0 to 0.68, that is a ratio, let me get my calculator, 2 divided by 0.68 of 2.941. 2.941. Since the nitrate and the oxide have the exact same coefficient, a 2-to-2 ratio, we actually don't even need to multiply anything. If we use the mass of the group 2 oxide and make a ratio with the molar mass of the nitrate, will also, whatever gets closest to this number, will be your right answer. That's another way of doing this. Now, what's its downside to doing it that way? These oxides all have different molar masses. So unlike here, where we multiply by this or divide by the same number, we'll have to multiply them, or divide them, sorry, by different numbers, but we won't have to figure out all of these coefficients. So both of the ways have merit, both of them will give you the right answer. So you can go ahead and do whichever way makes sense to you, but that's the thing, it needs to make sense. And that's the part that's going to be difficult, is trying to make this make sense. All right? Because it is a lot of critical thinking. This question is a high level of critical thinking. And if you don't understand the ratios, I would definitely leave a question like this for the end of the test instead of trying to tackle it right away. So let's go back to our PowerPoint here. So if we go here, we see that the answer to this problem was indeed what we ended up with, which was B. All right. So that just goes to show you how complex the critical thinking in these questions can really get. Now, did we use anything new? No. Everything we used was molar masses, mole ratios between the chemical formula and the reaction, sorry. The only thing that was new that you might not be able to figure out was the reaction itself, but you'll be able to do that once we go over in organic chemistry. All right. Later on, I will have you do those by yourself. If I were to give you this question on a test or a quiz, then I will give you those problems right now, or those reactions, those formulas. So, a few things that we need to consider here for this mathematics. All your answers for this Cambridge course should be given to the lowest number of significant figures in the data was used in the calculation. So this goes back to significant figures from honors chemistry. You should be using those significant figures. A lot of the time, because we're just multiplying and dividing, then your answer is going to match in significant figures to the number given to you in the question that has the lowest number of them. Do not round numbers to the correct number of significant figures until the very end of your calculations, because you risk introducing error. When we're doing work like this, we leave the rounding for the very end. We round our final answer to the correct number of significant figures. Because if you do a step and then round, and then do a step and then round, and do another step and then round, you're introducing what we call rounding error. Every time that you round, you introduce error into your work. And so by the end, that error accumulates and may give you the wrong answer. Remember that you must round to the right number of significant figures, not just cut off the number. So if that last digit needs to be rounded up, you should be rounding it up. So a bit of a refresher. If there is a decimal place, you're going to count the numbers from left to right, starting at the first non-zero number in order to figure out the significant figures. So for example, we have something like 0, and I'm using black so you can't see it. So let me use a different color. So if we're getting something like 0.002408, because there is a decimal number here, or a decimal place, we're going to start counting from left to right at the first non-zero number. In this case, the first non-zero number is 2. So this number has 2, 4, 0, and 8 are the 3 significant figures, or 4 significant figures. So this number has 4 sig figs, 4 significant figures. Again, if there's a decimal, we go from left to right and we start counting at the first non-zero number. If there is not a decimal place, we count from right to left and we do the exact same thing. We start at the first non-zero number. So if the number, for example, is 408,100, right? We're gonna go from right to left, starting at the first non-zero number, which is 1, and then count all of the digits. 1, 2, 3, 4. So this number also has 4 significant figures. So we start counting at the first non-zero number regardless. If there is a decimal place, we go from left to right. If there is not a decimal place, we go from right to left. And then just remember basic rounding. If we have a number like 526.84 and we want to round it to 4 significant figures, we would go to the fourth, 1, 2, 3, 4 significant figure. If we're going to cut it off here, we look at the next number to see if we round at 8. Since the number is below 5, we do not round, so that number stays 526.8. Now, if we're rounding to, let's say, 3 significant figures, again, we're going to go from left to right, find that third, so 1, 2, 3 at the 6, that's 3 sig figs. And then we look at the number, the next one is 8, so this is above 5. So we need to grab this 6 and round it up to a 7, to 527. And then finally, if we're going to do 2 significant figures, same thing. We're going to go for 2 significant figures. That's 5 and 2. We're going to cut it off here. So since the next number is a 6 and it's above 5, or 5 or above, should I say, we're going to grab this 2, round it up to 3. So that is going to be 530. Be very careful. The answer is not 53, because 53 and 526.84 are nowhere near the same number. When we're rounding, if we got to round and get rid of some digits before a decimal place, we need to convert them to zeros. Why? This 0 is not significant. So 530 only has 2 significant figures, but it keeps the magnitude of the number, so in the hundreds instead of the tens. All right. So that's just a review of how to answer these math questions. Let's review another thing from honors chemistry, which is percent composition by mass. The percentage of the elements by mass that are in a particular compound is the percent composition by mass. So, for example, if we have C6H8O7, which is an organic compound, which you could see on your test because we will study organic later in the year, how much of the mass of this compound comes from carbon? What percentage comes from hydrogen? What percentage comes from oxygen? That's what we're talking about when we talk about percent composition, and we're always talking about the mass. That number can be found using the chemical formula of a compound or by using stoichiometry to convert from masses of a product to masses of the reactant. Both of these are very common questions on the AS test. But in general, it's always the same thing. The percent composition is going to be the number of moles of that element times the molar mass divided by the molar mass of the compound. Now, if we want to do it by grams or by mass instead of by molar mass, it's the same thing, but it's the number of moles of the element times the mass of that element that we have divided by the mass of the compound. So I'm going to show you an example of both of these. But essentially all we're doing is, okay, so if we have carbon, for example, carbon has a molar mass of 12 times 6 carbons in the compound. That number divided by the molar mass of the compound as a whole, that is its percent composition, which will be 37.53. So in this case, again, if we wanted to do this for each one of these elements, carbon has a molar mass of 12 and there are 6 carbons. Hydrogen has a molar mass of 1 and there are 8 hydrogens. And oxygen has a molar mass of 16 and there are 7 oxygens. So if we bring over our trusty calculator, where did my calculator go? Oh. My calculator closed itself. 1, 2. So, and if I bring over my calculator, we have 12 times 6 plus 1 times 8 plus 16 times 7. So let me do this. 16 times 7. Oh, let's do that again. 12 times 6 plus 8. 1 times 8 plus 16 times 7 gives us 192 is the molar mass of the compound. So we have here 192 grams per mole is the molar mass of the compound. I want to know the mass of carbon. All I have to do is 12 times 6. So carbon will be 12 times 6, the molar mass of the carbon times the number of carbons, divided by 192. If I wanted to know hydrogen, I would just do 1 times 8, again, molar mass of hydrogen times 8 hydrogens in the compound, divided by 192, which is the molar mass of the compound. And if I wanted to know oxygen, I would just do 16 times 7, divided by 192. So if I do this, I should get the molar mass of each compound in a decimal. So in order to transform this to a percentage, like you always do with percentages, we would multiply by 100. Otherwise, we get the decimal form, which is helpful, but when you want the percentage, we always need to multiply by 100. So this will be 37.53, like it says on the graphic, percent. This will be 4.16% hydrogen, carbon, and this will be 58.29% oxygen. So what does this mean? 37.53% of the mass of this compound comes from carbon, 4.16% of the mass of this compound comes from hydrogen, and 58.29% of the mass of this compound comes from oxygen. So let's look at our next problem here, which is going to use this. Which calcium compound contains 54.1% by mass of calcium? So here, again, we're looking at the percent composition, but we're looking at it as a paper 1 question, which has different options. So again, using those options is going to be your best bet every time. And there are actually 2 different ways of doing this here. For both of the ways that we're going to do this, we need to use the molar masses. Now, we are going to kind of do this the long way because we're going to do every single option. But you're actually going to see that had we just gone down the list, these would have been a lot faster if we didn't do them all at once. And that's something that is going to happen fairly often. So first of all, I'm going to bring this over here so we have a working problem. And we are going to need the molar mass of our compounds. So first of all, in order to know the molar mass, we need to know what these compounds are. And that is going to require you to remember some nomenclature from honors chemistry. So calcium hydroxide is CaO2, OH2. Because remember, calcium is a group 2 element. So we have hydroxide ion, which is OH minus. Calcium has a 2 plus ion. When we cross them, we get CaOH2. Calcium nitrate. Again, nitrate is NO3 minus. So again, it's a 1 to 2 ratio. So CaNO3 2. Calcium oxide, which is just calcium with oxygen. They're both -2 and +2, so it's a 1 to 1 ratio. And then calcium sulfate is CaSO. Oops, no parentheses there. It's just CaSO4 because calcium and sulfate both have a 2 charge. 2 plus for calcium, 2 minus for sulfate. So we need the molar masses for all 3 of these. So we have calcium hydroxide. Molar mass of calcium is 40.1 plus 2 oxygens, so 16 plus 16, because there's 2 oxygens, plus 2 hydrogens, so 1 plus 1. Gives me a molar mass of calcium oxide of 74.1. 74.1. And again, just as a reminder, the molar mass of calcium, which is in all of these compounds, is 40.1 grams per mole. And we'll leave that there because we're going to need it. Calcium nitrate. Molar mass of calcium nitrate is going to be based on, again, we have calcium, which is 40.1, plus nitrogen. Molar mass of nitrogen is 14, and because of that subscript, there are 2 nitrogens in here. Plus the molar mass of oxygen, which is 16, times the number of oxygens, which in this case is 6. So here we have the molar mass of calcium nitrate, like it was in our previous questions, 164.1. Next is calcium oxide, which is much easier because we just have calcium, which again is 40.1, plus oxygen, which is 16, is 56.1. So 56.1. And then finally, calcium sulfate. Again, we have calcium, which is 40.1, plus 1 sulfur, whose molar mass is 32.1, plus we have here 4 oxygens. Our molar mass of oxygen is 16 times 4 gives us 136 point, oops, I lost what it was. 136.2 as its molar mass. So we can do this one of 2 different ways, and I'm going to show you both of them. The first way of doing this is just by you doing the ratio. All of these have 1 calcium. So in order to do this, we could just do the molar mass of calcium divided by the molar mass of the compound to get the percentage. So here this will be 40. Oops, let me erase that and do a little better. 40.1, which is the molar mass of calcium, divided by 74.1 times 100 to get the percentage. This will be 164.1. Oh, oops. This will be 40.1 divided by 164.1 times 100, again for the percentage. This will be 40.1. Okay, I keep trying to do it backwards. 40.1 divided by 56.1 times 100. And this will be 40.1 divided by 136.2 times 100. So whichever one of these gives us 54.1, that's our right answer. And this is why I said we're going to do this the long way. Because look, 40.1 divided by 74.1 times 100 gives us 54.1. So our answer is actually just A. Did we need to find the molar masses for all these? No. Had we just gone down the list, we saw A was the right answer. We could have just stopped there and moved on to the next problem. But just so we are aware, just so for the fact of learning, if we do all of this, 40.1 divided by 164.1 times 100, this will be 24.4. And again, these are the percentages by mass. If we did calcium oxide, we will have 40.1 divided by 56.1 times 100 is 71.5, because again, rounding. So 71.5%. And then if we did calcium sulfate, we will have 40.1 divided by 136.2, which will be, times 100, 29.4. So 29.4 here. So you can see that the only one that gives us an answer that is even close to the percentage that we had was A. Now there's one other way of doing this, which you could choose to use. And again, there is no right way of doing this. Both of these are perfectly fine, which will be to multiply the decimal version of the percentage by the molar mass and see which one gives you the molar mass of calcium. Because if we do, which is essentially just rearranging this equation, if we do 74.1 times 0.541, we get, what's my calculator? 74.1, which is the molar mass of calcium hydroxide, times 0.541, we get 40.09, which is very close to the molar mass of calcium. This will be the right answer. If we do it, I'm going to do it for one more. I'm not going to do it for all four because it will just be a waste of time. But let's do it for the last one. If we do 136.2, which is a molar mass, times 0.541, again, that will be 136.2 times 0.541. That gives me 73.7. 73.7 is nowhere near the molar mass of calcium. So this is another way of doing this. We could do this for all four of them. Only the first one gives us a molar mass of calcium, so that's the right answer. Either of these two ways of doing it is fine, especially because it's a multiple choice question, and you will get full credit for doing this in either of these formats. So that is another paper one question that uses percent composition. And we can see here that our answer was indeed the A. All right. So that's another way. Now, had they given me not a percentage, but given me masses, you should also be able to do this, which we might see in our practice problems later on. Now, types of formulas. This is something that you should know from honors chemistry. But there are two types of formulas that we can use in chemistry. It's actually more, but we'll start with these two basic ones. There's empirical formulas and molecular formulas. An empirical formula is the simplest whole number ratio of the elements present in one molecule or formula unit of a compound. Now, what this means is that what we're looking at is just a simplified ratio. We're looking at a ratio of the elements in that compound. Whereas if we're talking about the molecular formula is the total number of atoms present of each element in one molecule or one formula unit of the compound. Now, the molecular formula tells us the actual number, meaning it's not simplified. Whereas the empirical formula, because it's a ratio, may be simplified. So one way to think about this is that this is simplified while this is not simplified. These molecular formulas are usually used for covalent compounds, while the empirical formulas are usually used for ionic compounds. Now, we can use the empirical formulas for molecular compounds, but they're usually used in work to figure out something else. We do not give molecular compounds as empirical formulas normally because there's multiple molecular compounds or covalent compounds that may use the same formula, empirical formula. Whereas ionic compounds are always given as empirical formulas because they're always simplified because they don't form individual molecules. They form these giant crystals that we talked about last year. Now we can see here some examples of this. Water's empirical formula is H2O, as was its molecular formula, because a 2-to-1 ratio cannot be simplified in whole numbers. So both empirical and molecular formula are the same. On the other hand, hydrogen peroxide, H2O2, does have a difference in the molecular empirical formula. H2O2 is a 2-to-2 ratio that can be simplified to a 1-to-1 ratio. So H2O2 is a molecular formula of hydrogen peroxide, but the empirical formula is HO. This is important that we give the empirical or the molecular formula for hydrogen peroxide. Why? Empirical formula of HO could be multiple different compounds. It could be H2O2, H3O3, H4O4, so on and so forth. Now, with the inorganic compounds like this, it doesn't usually matter. So you can see sulfur dioxide, also with 1-to-2 ratio, can be simplified. But once we start talking about organic compounds, especially later in the year, like butane and cyclohexane, it's going to become very important to know the difference between a molecular formula and an empirical formula. Because, for example, butane has the molecular formula C4H10. That's a 4-to-10 ratio, which can be simplified to a 2-to-5 ratio. Well, even though butane, C4H10, has its empirical formula, other compounds with this empirical formula could include things like C4H10, which is butane. We could have C6H15, which is hexane. We could have C8H20, which is octane, so forth and so on. So these are actually actual compounds that exist, all with different molecular formulas, but the same empirical formula. And so it's very important for us to make sure that when we are doing molecular compounds, we use the molecular formula so we know specifically which one we're talking about. Because if we use the empirical formula, we might be talking about a bunch of different compounds in organic chemistry that all exist, but we're not being very specific. So how do we find the empirical formula from data? Because this is something that you could be asked to do, and it's actually kind of related to percent composition. We can use combustion data or percent composition data in order to calculate the empirical formula of an organic compound, which is something that you're going to see very commonly on the AICE exam. We could do it for inorganic compounds as well, but it is more common to do this for an organic compound. So how, if we're given combustion data or percent composition data, how would we go about converting this to empirical formula? Well, like we said before, it's a matter of ratios. If we're given percent data, the very first thing we want to do is convert that to mass, convert that to grams. And we do this by essentially just assuming we have 100 grams of that compound. So if we add 20% carbon, 20% becomes 20 grams. If we have 30% carbon, 30% becomes 30 grams. If we have 22% hydrogen, 22% becomes 22 grams. And that's why we assume we have 100 grams. Makes life easier. Once we have those grams, we can convert each element to moles by dividing their masses by their molar mass. So we can convert the grams of each element to moles. Now, if we're given combustion data, this first step looks a little different, because we find the grams of the elements by looking at the different compounds that they give us. But we'll see that later on. Once we have the moles of each element from their molar, by dividing them by the molar mass, we can divide the resulting moles by the smallest one of the answers, by the smaller one of the moles, to get a mole ratio. And now we did this in honors chemistry, where we found the mole ratio between all the elements by dividing by the one we have the least number of moles of. We then use the resulting mole ratio as a subscript in the empirical formula, because that's what the empirical formula is. The simplest mole ratio between all the elements. Now, rounding might be necessary, right? We might not get the exact number that we're looking for, but that is something that you should now be comfortable with from honors chemistry. You're rounding your answers to a number that would make sense for your calculations. So let's look at an example of this. Here we have a question from paper 2. Analysis of another organic compound, B. So again, why another? Because this is part of a bigger question that probably use different parts or a different organic compound, probably called A. But we don't really care about that part. Analysis of another organic compound gave the following composition by mass data. We have 64.86% was carbon, 13.50% was hydrogen, and 21.64% was oxygen. Use these values to calculate the empirical formula of B. So essentially, they're giving us percent data and asking us to calculate the empirical formula of this compound. So let's again bring this to a working environment. So let me grab this. So analysis of another organic compound B gave the following composition masses. We have the percentages, and then use these to evaluate the empirical formula of B. Now here is where these are going to be a little different from question to question. What you're given will be different. Here we're given percentages. In a different question, we'll see that maybe we're given grams, and so we don't need to do the first step of converting. In another question, we might be given the amount of carbon dioxide and water created, and then we'll have to figure out the amount of each one of these elements. So know that these questions are going to be varied. If I made an example of each type of question, we will be sitting here forever. This video is already long enough. We will be sitting here for even longer. So critical thinking is going to be essential for this chapter and specifically this section. So here, for example, we have carbon, we have hydrogen, and we have oxygen. They're telling us that we have 64.86% carbon in this compound, 13.50% hydrogen, and 21.64% oxygen. Well, how do we convert this to a working number? How do we convert this to grams? Easy. If we assume we have 100 grams of B, and again, we could assume whatever we want because they don't tell us a specific amount. But if we assume we have 100 grams of B, 64.86%, because this is composition by mass, 64.86% mass of 100 grams is simply just 64.86 grams. And that's what we're doing here. We're assuming we have 100 grams of this sample so that the percentages just become grams. If we have 13.50% hydrogen, that means we have 13.50 grams of hydrogen in 100 grams of the sample. And if we have 21.64% oxygen, that means that 100 grams of the sample have 21.64 grams of oxygen. So this is the first step, is to get a working number, which is usually grams, sometimes moles, but usually grams. And now the second step is going to be to divide these by their molar masses so that we can get number of moles, because we want a mole ratio. So we want these to be converted to moles. Molar mass of carbon is 12.0 grams per mole. Molar mass of hydrogen is 1.0 grams per mole according to the Cambridge periodic table. And molar mass of oxygen is 16.0 grams per mole. So here we are just going to use our calculator. So 64.86 divided by 12 is 5.405. So here we have 5.405 moles. 13.50 divided by 1 is simply just 13.50 moles. And then 21.64 divided by 16 is 1.35, and we'll keep it to 3 decimal places, 1.353. So we have here 1.353 moles of oxygen. Now the next step is to get the ratio. So what we did right now was to convert to number of moles. The next step is to actually get the ratio. How do we get a ratio between numbers? Well, all a ratio is the number divided by the smallest of all of them. So the smallest out of these three numbers is 1.353. So what I'm going to do is I'm going to divide all of this by 1.3. Oops, I made those numbers backwards. 1.353 moles divided by 1.353 moles and divided by 1.353 moles. The moles here cancel, and what we end up with is a ratio. Now, this ratio may need to be multiplied, or it might not be. We'll see that in a second. But here, 1.353 divided by itself is just going to give us 1. 13.50 divided by 1.353 is essentially going to give us 10. Because again, sometimes you'll need to round this. If we look at the calculator, 13.50 divided by 1.353 is 9.9778. That's essentially 10, right? We need to be comfortable with saying, oh, that's just rounding error. That's just experimental error. We essentially have a ratio of 1 to 10 there. And then the last one, 5.405 divided by 1.353 gives me 3.99. Again, basically 4. So here we have a 4 to 10 to 1 ratio. And that's a ratio we're going to use in our empirical formula. All we got to do now is say, okay, we have in the ratio carbon has 4, hydrogen, draw that a little closer. Hydrogen has 10, and there's only 1 oxygen. So the empirical formula for this compound is C4H10O. Again, how do we know this? Because of the math. Now, let's say one of these was 1.5. Then we will need to multiply them by 2 because we will need a whole number ratio. Sometimes when we get decimals here, we'll have to multiply all of the ratio by that and multiply a whole number multiplier to get rid of that decimal. But this wasn't the case in this question. Our answer here is C4H10O, and so if we go back here, we can see that worked out. We get 1 point for the actual math. So here we see that we get 1 point for the math of dividing each one of the percentages, that which we convert to grams, by the molar masses to get the moles, and then doing that mole ratio, so it equates to 4 to 10 to 1. So we have 1 point for the work, 1 point for the answer, which is C4H10O. And notice, we do need that answer. If you just left 4, 10, and 1, if you just did your work and didn't show this part, then you wouldn't get that last point, because the last point is for the actual empirical formula, not the ratio itself. So C4H10O is necessary, not just 4 to 10 to 1. So that's an empirical formula question. Now, we can also have a question where we were asked to convert the empirical formula to the actual molecular formula. That is going to include more steps. In order to convert the empirical formula to the molecular formula, we need to first find the empirical formula like we just did, and then use the molar mass of the molecular formula, which is going to be given to you in the question, to find the molecular formula. So we need the molar mass of that molecular formula. That should be given to you in the question in order to do these type of questions. So we're going to divide the molecular formula by the molecular formula mass by the empirical formula's mass in order to get a ratio of their masses. Because remember, the empirical formula and the molecular formula are related. The molecular formula is a multiplied version of that empirical formula. So by dividing the mass of the molecular formula by the mass of the empirical formula, we're trying to see what do we need to multiply this by? What is the ratio of their masses? And then we multiply the atoms in the empirical formula by the number, by the ratio, in order to get the answer to what is the molecular formula. So there's an example like that here. We have 0.2 moles of hydrocarbon undergo complete combustion to give 35.2 grams of carbon dioxide and 14.4 grams of water as the only products. What is the molecular formula of this hydrocarbon? Now, this is a more complex question. Why? We are being asked for the molecular formula, but we're not being given the mass of the molecular formula. We're instead given masses, not molar masses. And we can still work with this. Those ratios should still appear when we work with these masses. So, again, there are a few ways of doing this. We can use those ratios that we, or those answers that we see here, because it's a paper one question. But we'll do this the long way, and then we'll do it, or we'll look at doing it the short way. But let's look at this question. Now, again, there is a few different approaches we can take to this, and the important thing here is the knowledge base is what we showed before, those what the empirical formula is, what the molecular formula is. But realize that not everything's going to follow the same steps that I showed you. Using critical thinking to figure out questions like this is very important. This is probably one of the hardest questions that we've done so far. So let's look at it. So first of all, this is a question that is a reaction, right? So we should look at it in that light. So let's look at the reaction itself. We have 0.2 moles of a hydrocarbon. Now, if you look at all of these, hydrocarbon, even though we haven't went over what that word means yet, we can see that all of these answer choices are carbon and hydrogen. So again, use your answer choices, even though you will learn what a hydrocarbon is later on. We have C and H are what hydrocarbon is made of, carbon and hydrogen. So the name makes sense. But the difference between these is that the subscript is different, CXHY. So we have this hydrocarbon, so it could be any of these, so we're just going to say CXHY, undergoes complete combustion. Now, we should know what a combustion reaction is from honors chemistry. We know that a combustion reaction is when something reacts with oxygen, O2, and in this case, it's going to create two things. Carbon dioxide, which they tell us, so they give us the products, CO2, and water, which is the other product, H2O. Oh, let me put that a little farther to the side. So we're going to have this hydrocarbon reacting with oxygen, creating water and carbon dioxide. Now, here's the hard part. How do we balance a reaction that we don't know what one of these reactants is? We just know that it's made of carbon and hydrogen. You have to think of the law of conservation of mass. And you have to think of where these elements go. Because that's, again, the critical thinking is really high level, but that's what this expects of you. Because if we think, we have CXHY. We have X moles of carbon. Where do those carbons go? If we look at the products, there's only one product with carbon in it, CO2. So all of the carbon here has to go to CO2. And that means that if we have X number of carbons here, they're all going to be in carbon dioxide, which has 1 carbon per mole of carbon dioxide. So if we have C2, then we need to make 2 moles of carbon dioxide, because that will give us the 2 carbons. If we have C4, then we need to make 4 moles of carbon dioxide, because that will give us the 4 carbons. So what we can do is, instead of saying C, instead of putting a coefficient in front of the carbon dioxide, we can use this X as a variable, meaning we have X CO2s, because that's where all of these CO2 is coming from, this carbon right here. Same thing with hydrogen. With hydrogen, we have this Y that we use to symbolize its subscript. Well, where does all of the hydrogen go? All of the hydrogen goes to water. But there's a difference here. Why? There are 2 water atoms in 1 molecule of water. Or another way to see that is that we have 2 moles of hydrogen in 1 mole of water. That means that if we have, for example, H8, we wouldn't have 4 water, or 8 waters, we'll have 4 waters, because each water will have 2 hydrogens. If we had H10, we will have 5 waters, because 5 times 2, it would be 10. So what does that mean? That means that the coefficient for the water is not going to be the same as the subscript for the hydrogen. It's going to be half of that because of this H2. So we can symbolize this as Y over 2. Because again, if we have H10, 10 divided by 2 is 5. 5 times 2 is 10 hydrogens. If we have H8, 8 divided by 2 is 4. 4 times 2 is 8 hydrogens. So on and so forth. So that gives us a working equation, a place to start. And that's the important thing here is when you get stuck, find a place to start. So here we're told we have 0.20 moles of these compound reacting, and that those 0.20 moles of this compound reacting make 35.2 grams of carbon dioxide and 14.4 grams of water. Now here is where this is going to kind of take us somewhere. Why? We can use these numbers. We can convert these numbers to ratios, to moles that are workable. And then from there, figure out which of these molecular formulas would actually work. Why? We can look at the ratio or the moles of carbon and hydrogen created here. We can look at oxygen. Why not? Because this oxygen is going to be some amount, right? We should have a coefficient here, but we don't know what the coefficient is because both carbon dioxide and water have oxygen in them. So we don't know what this coefficient is. So we're going to focus on the carbon and the hydrogen in order to solve our problem. So first of all, we know we have 35.2 grams of CO2. The first thing we always do when we're working with grams is convert this to moles to make it easier to work with. The molar mass of carbon dioxide is 44.0 grams of CO2 is equal to 1 mole of CO2. Now, we now have moles of carbon dioxide, but we don't want moles. We want of carbon dioxide. We want moles of carbon, right? Because that's what we're going to work with. So here we have, if we have 1 mole of carbon dioxide has 1 mole of carbon in it, CO2, right? So C1. So 1 mole of carbon dioxide is 1 mole of carbon. That means that these 35.2 grams of carbon dioxide represent, so we have 35.2 divided by 44 times 1. It represents 0.8 moles of carbon. Why is that important? This is important because where did all of these 0.8 moles of carbon come from? They all came from these 0.2 moles of the hydrocarbon. That is the only place carbon could have come from. If we do the same thing with hydrogen, we have 14.4 grams of water. Molar mass of water is 18. So 18 grams of H2O is equal to 1 mole of H2O. But again, we don't care about the water specifically. We care about the hydrogen in the water. So we know, thanks to y over 2, that, and thanks to the formula itself, H2O, we know that 1 mole of water of H2O has 2 moles of hydrogen in it. Again, that's where this y over 2 came from, because of the 2 in the water, because of that ratio. So we have here that, again, we're going to bring our calculator over, 14.4 grams divided by 18 grams per mole of water times 2, because there are 2 atoms or moles of hydrogen per mole of water, that gives us 1.6 moles of hydrogen. So here we have 1.6 moles of H in this compound. So that means that all of these 1.6 moles of hydrogen came from this. Now, that alone is enough to narrow this down. Even if this is as far as you got, you have to think about it. You have twice as much hydrogen as you do carbon in this compound, meaning that it couldn't be C, because C has a 1-to-1 ratio between carbon and hydrogen. It could be D, because there is a 1-to-2 ratio. It could be A, because it has a 1-to-2 ratio. But again, it couldn't be B either, because the ratio is a 2-to-6 or a 1-to-3 ratio here. Again, this is a 1-to-1 ratio. So we can, just by getting this far, we can actually eliminate B and C. So even if you just got this far, you just made your chances from a 1 in 4 to a 1 in 2, a 50% chance of getting the right answer. Now, how do we actually get the right answer? going back to what we talked about, molar masses and molecular masses, we need to look at the ratios. We need to look at the ratios of the carbon and the hydrogen in these. Let's go back here. We need to look at the ratios of carbon and hydrogen in this compound to the moles of the compound itself. So what are we going to do? We're going to do ratio. How do we do ratios? We divide things, right? So we're going to divide the amount of each element by the amount of the compound. It's the same thing that we would do with the molar masses, but now we're using the actual numbers from this problem. So we have here 0.8 moles of carbon to 0.2 moles of the compound, which we'll just call this X, because we don't know what this compound is. So 0.8 divided by 0.2 should be 4. We do the same thing with hydrogen. We have 1.6 moles of hydrogen divided by 0.2 moles of this compound X. 1.6 divided by 0.2 gives us 8. So it's in this formula a C4H8 formula, meaning that the answer has to be D, not A. Again, how do we know that? We're doing a ratio between the mass of the compound. So this is an empirical formula because this is the actual, not mass, number of moles of compound. This is the actual number of moles of the compound, so it's not empirical, this is molecular, divided by the number of moles that are actually in that compound of the carbon. So 0.8 of the carbon divided by 0.2 of the compound, that gives us a 4, which is the coefficient. And then we do the same for the hydrogen to get the 8 coefficient. Again, is every question you get going to be like this? No. If I went through every type of question that we could possibly see on the exam, I would make a 5, 6, 7, 8 hour video because there's so many different stoichiometry questions. There's so many different types of questions that can be asked. This is not, the importance here is not learning steps. The importance here is realizing the actual critical thinking behind this, the actual thought process behind solving these problems. And that's what you need to focus on. You need to practice these problems until you get good at thinking critically and putting everything you know together to get to the answer. All right, so this is it for section 5. We will keep working on these as we do practice problems throughout the course. But again, the importance here is practice so you can develop the critical thinking needed for stoichiometry, because that's what's going to really get you on the AICE exam. Can you think critically and solve the puzzle, not just memorize what you were taught? That's it for today. I will see you all in the next video where we'll cover section 6.